Okay, had a little break in the action there. This is the second video. But we're going to pick up here where we cut off at full load amperage and having dual voltage motors. These motors are come equipped for maybe 2 different voltages, so you can use them in more than one application. And you may have this is just an example of a motor that may be rated for 230 volts or 460 volts. And we're just pretending that it's probably more than likely it's going to have to be a 3-phase motor here. So you can see that it'll have a full load amperage rating listed under each voltage. And if you'll notice, if it's 230 volts, it may have a full load amperage rating of 5. And if you power it up to 460 volts, you may have a full load amperage rating of 2.5. So notice the calculation and the difference here. The higher the voltage you send to the motor, the lower the amp draw, okay, vice versa. So that's very important to know, because in certain buildings you may not have exactly 460 coming to your motor. So it's important to know what your measured voltage is in order to calculate what your corrected full load amps might be. We may not have 460 coming to the building. It may be a different voltage. That's where we come into what we call a corrected full load amp calculation here. Okay. Now the calculation for that is, this stands for corrected full load amps. This equals the rated voltage over the actual voltage times the rated full load amps. We're trying to come up with an exact number here. Okay, an exact number according to the exact voltage that we have fed into the building. All right, and this is the formula that we want to use. Now, I listed an example right here where it may be pertinent. Especially if you have a motor. If you have a motor rated for 6, and then let's say you're drawing 5.9 amps or right at 6 amps, and you're worried about overloading the motor. You want to use this calculation to make sure that you're okay here, because you don't want to overamp the motor, and you don't want to have the motor burn out and have a shorter life. So using this calculation, we have an example. The rated voltage of the motor is 460 volts, but the actual voltage that we have coming into the building at the motor is 475. Now if it's 3-phase, you'll have to remember, maybe we're getting something like on one leg, we may be getting from L1 to L2 478. Then we may be getting 473, and on L2 to L3, L1 to L3, we may be getting 475. So what we have to do here, we'll get 3 readings, and we have to divide these numbers, okay? We have to add them and divide them by 3 to get an average. So that's what we've done here. Add them and divide it by 3 and get an average actual voltage of 475. Now, 460 divided 475 times the full load rated amps on the motor will give us 5.8. So now we change this number, and it's a minimal change, but it could be pertinent. We changed the 6 full load amp rating to a 5.8. So that's very important, especially if we were actually drawing, if we're drawing 5.6 amps, we don't have anything to worry about. But if we're drawing 6 amps, and then we've done our corrected full load amp equation, and we come up with 5.8 is the highest amperage we ought to be running without getting into the service factor, then we may need to make adjustments to the pulley or the sheaves to make sure that we get this amp draw lower than its corrected full load amp rating.
Is that it?